Good morning and welcome to the continuation of turbulence modeling in computation heat and fluid flow. The last thing we saw yesterday was the Boussinesq approximation, and there we need the eddy viscosity to determine that, and we need to determine the turbulent kinetic energy. So, before we come to what is here on the screen, we first do a little bit of work to get the values to determine the eddy viscosity and the turbulent kinetic energy. And for that, we need two transport equations. When we use a two-equation model. And they are derived then to determine the eddy viscosity mu t and the turbulent kinetic energy k. Those are appearing in the Boussinesq approximation. And the most popular two-equation models is the K epsilon model. And that is due to Jones and Launder. From 1972. Yesterday I mentioned also the work where Launder, Rees, Rodi were involved. I said that it was at Manchester, it was wrong, it was at Imperial College in London. Later on, Launder moved to Manchester, where I think he is still now. So in this model, the K epsilon model, we use a transport equation for the turbulent kinetic energy and for the dissipation rate. So there we use transport equations for the turbulent kinetic energy and that is the K in the model, and the dissipation rate, and that is the epsilon. And the first equation is then the equation for the turbulent kinetic energy, and that can be derived actually when we look at the Reynolds stress mods that we discussed yesterday. Then we had actually if we take the trace then of this tensor that we would get, then we would get close to the turbulent kinetic energy with a minus and so on. And what we get in the end is then the following. It is the time derivative of the density times the turbulent kinetic energy plus, and then we have the convective flow, and that is described in this differential form by the divergence of, in our case, the constant density times the mean velocity vector u bar times the turbulent kinetic energy. And on the right-hand side, we have the diffusive flow of the turbulent kinetic energy, and that is then described in differential form by the divergence of, and now we have here the viscosity, or laminar viscosity, plus the turbulent viscosity, mu t, that we still need to determine, divided by the sigma k. That is just a parameter. And then that is multiplied by the gradient of the turbulent kinetic energy. And then we have in addition a term describing the production of turbulent kinetic energy, that is the tau r, that is the Reynolds stress tensor, and we have the dyadic product, I tell you later what that is, with the tensor velocity, that is the gradient of the mean velocity. So that's a tensor. and that describes the production rate of turbulent kinetic energy, and then minus rho epsilon, and that is the dissipation rate. So now we can look at the individual terms, what they signify. So the first one is the rate of change. And that is, it will all at the end be of turbulent kinetic energy. So, and this will be the convective flow. Of turbulent kinetic energy. This will be described the diffusive flow. Of turbulent kinetic energy, and this is then the production, and this is the dissipation. And that is all the rate of so the production rate of turbulent kinetic energy and the dissipation rate of turbulent kinetic energy. So that is the K equation, the equation for the turbulent kinetic energy. So that is this one that we consider here. And then in addition we have then an equation for the dissipation rate. Now I have to tell you this, what is this dyadic product here of the Reynolds stress tensor and the gradient of the mean velocity vector, and that is the following. So the tau r, dyadic product, nabla u bar, that is the sum over all indices ij, where we take the components of the Reynolds stress tensor r tau ij r. Remember that is minus rho u I prime u j prime averaged times the derivative of u I bar with respect to xj. So that is a number in the end. And the sigma k that is appearing here, that is chosen as 1. So that is then the model that Jones and Launder use for the turbulent kinetic energy. And you see it is a transport equation, time derivative, a convective flow, a diffusive flow, and a source term, which has two parts. One is producing, one is dissipating turbulent kinetic energy. In a similar way, we have a transport equation then for epsilon, the dissipation rate, and that looks like that. That is now the following, that is then equation 15. There we have a time derivative of rho epsilon, and we have a convective flow described by the divergence of the constant density times the mean velocity vector times the dissipation rate epsilon. And that is equal to, and then we have the divergence of, and now we have something similar as we had there. We had the viscosity coefficient mu plus the turbulent or eddy viscosity mu t divided by some other constant sigma epsilon times the gradient of epsilon. So that is then describing the diffusive flow, and now we also have here some production and dissipation of the dissipation rate. And that is described now in the following way. Another constant, C1 epsilon, epsilon divided by K, turbulent kinetic energy, and that is then multiplied by the term that we had already here for the production of turbulent kinetic energy, that is tau R, Reynolds stress tensor, dyadic product, with the nabla of the mean velocity vector. And then we have also some dissipation here of the dissipation rate, which is C2 epsilon, and that is then rho, and here we have then epsilon squared divided by k. So, and here we can also identify then the physical meaning of each term, and that is the rate of change. The rate of change, and that all will be of dissipation rate. And here we have the convective flow of dissipation rate, convective flow, and here we have the diffusive flow, and here this describes the production, and this describes the dissipation. The dissipation rate of, so here this, that, and well, that is rate of, and all is then the rate of dissipation rate. So we have a production rate of epsilon and a dissipation rate of epsilon. So these are then the equations, and these coefficients or these parameters are chosen as follows, and they were chosen to fit experiments. So Jones and Launder, they did a couple of simulations and got then these fitted parameters. And they chose the following. These numbers are not important to remember at all. It's just that you know where they come from. So they come from fitting experimental data. And the sigma epsilon is 1.3. Let's see. Yeah. So the thing that you have to imagine is, this is another transport equation, consisting again of time derivative, a convective flow, diffusive flow, and a source term containing production and dissipation. That is just the transport equation as we know how to solve. We know then we have just two transport equations, we solve them. In the end we get k and epsilon. When we have k and epsilon, then we compute the eddy viscosity in the following way. First thing to note is we have an equation for k, so then we can use that directly, because that is needed in the Boussinesq approximation. So that is a good thing. And now to get the eddy viscosity, then Jones and Launder, you do it the following way. So the eddy viscosity is computed in the following way. That is the eddy viscosity. That is determined by the following. That is 16. That we say the eddy viscosity is equal to the density, some constant, times the ratio of the turbulent kinetic energy squared divided by the dissipation rate epsilon. So, and this constant that was then chosen according again by fitting experimental data, Cu and 0.09. The important thing to remember is that the eddy viscosity is determined by means of the turbulent kinetic energy K and the dissipation rate epsilon. Those two equations that we solve here. So that is the standard K epsilon model that we have here. And that is frequently used to simulate turbulence. However, what we have seen here is the standard K epsilon model. So the standard K epsilon model that consists of the equations that we have just seen. Equation for K, equation for epsilon, and the equation for the eddy viscosity is not valid near walls. So, and usually, if you do it, we use so-called wall functions. That is an important concept to understand because that makes the computation of turbulent flow much easier, but it has restrictions. So they are used near the walls. And the wall function idea is the following. Imagine we compute flow over boundary layer flow, where we have say the surface, say of an airfoil, of a plate, whatever you can think of. It's easiest to imagine it's a flat plate. Of course, there we know already something. Then we plot on the abscissa the u bar, so the average velocity component in x direction, so that's the mean of the velocity vector component in the x direction, and we plot here now that versus y. We want to see what is the velocity profile. And what we usually have for the velocity profile is we have a very steep gradient near the wall. So it's extremely steep, and so it's following that very long, and then at some point it goes off. So that is supposed to be a turbulent velocity profile. And then you can imagine if we want to resolve things near the wall, we need extremely fine grids. With the approach of the wall functions, we don't need that. With the approach of the wall functions, we just say we try to get out of this region where things are happening very quickly, and we get to point, say, here we have the y equal to 0, and here we have, say, the first grid point, y1, and then we have some other grid points, say, y2, and so on. And so we have then the velocity vectors would be then like this. And the catch is now that we choose our grid points, our first grid point away from the wall, such that we are in the log-law region of turbulent flow. So let me tell you what that means. So that means the velocity u, in that case, the mean velocity u, is not resolved, as you can see in this sketch, between the wall, which is at y equal to 0, and the first grid point, y1. First node y1. But instead, this region is described by the classical law of the wall. So then we assume that the law of the wall, the log law, is valid. And that is the limitation of the wall functions. This is essentially only true for attached flow. For separated flow it is not true. And this is what you learn in fluid mechanics, that the velocity component of the mean flow with respect to the friction velocity, I'll give that in a moment, is equal to 1 over kappa von Karman constant times the logarithm of y plus some constant b. So in here, just to tell you the parameters, that is the u tau, is the friction velocity, that is the square root of the wall shear stress tau w divided by the density rho. So that is the friction velocity. In the direct numerical simulation from the Center of Turbulence Research, Stanford University and NASA Ames yesterday, I showed you, they used this to make to compute the Reynolds number. So they had the Reynolds, in the Reynolds number, the velocity based on this friction velocity. This gives usually lower values than you would have with if you would have a free stream velocity. So the tau w, as I said, that is the wall shear stress. If we would have just a simple boundary layer flow, it would be mu du dy. And then the other parameters, the y plus is a very important parameter, that is the non-dimensional wall distance, and that is the rho u tau times y divided by mu. So the non-dimensional wall distance. That is, the dimensional wall distance is y, and the non-dimensional is then this way. You see, this has it's like a Reynolds number. And the kappa, that is about, well, some people have it 0.4, others have it 0.41, the von Karman constant, after Theodor von Karman. And the B is a parameter that depends on your wall roughness, and for a smooth wall this is about 5.0. So the idea is simply that we assume this law is valid, and then we can bridge the gap from the wall to the first grid point. So we must, with that, be inside the log law layer. Yes?
What's the y in y plus?
The distance from the wall.
Okay.
That is the y. So y equals 0 is at the wall, and y is then, so this is the distance from the wall. Okay, so, and according to the Fluent manual, this y1 plus that we have here, so the y1 is then the dimensional distance from the wall of the first grid point. But when we look at the y1 plus, the non-dimensional distance of the first grid point of the wall, that should be between 30 and 300. So, and that is rather large distance compared to the usual turbulence models, where the y plus has to be smaller than 1. So here, for the application here, we should have the y plus, the y1 plus, or the first grid point, should be roughly in this range when we use the wall functions. So then the approach is such that once the velocity is known here, we can relate the turbulent kinetic energy and the dissipation rate at that point to the u tau. So let me write that. So once the velocity component is known at the first grid point, u tau, that is the friction velocity, is determined from the law of the wall. So can we see that? Yes. So imagine this is known, this is unknown. In the kappa, the B unknown, the y plus, we know the y, but we don't know the u tau. So we have a nonlinear equation for the u tau that we solve, then we have u tau. And if we have the u tau, then we have the wall shear stress. So then we have the viscous force in the tangential direction at the wall. So then in the log layer, where the law of the wall holds, the equations for turbulent kinetic energy and dissipation rate 14 and 15 simplify and yield, that is 18, the k of y1 gets u tau squared, square root of c mu, and the epsilon of y1 gets u tau to the power 3 divided by kappa y1. So then we have here these expressions, so then we can use them. So that is a way where you can save a lot of computing power, because then you don't need to resolve what you usually have to do. You have to go to y plus below 1. So here you can see you can choose it's maybe 200 or whatever. So you skip resolving the near wall region. That means you skip, you don't need a lot of grid points, and you don't need to have small grid sizes. They mean always long computing times, because when you have very small grid sizes near the wall, very large out, so that takes you a lot of time then for getting convergence. So that is, and you need less grid points, the computing time is less, faster convergence, so it has a lot of advantages. But it's only valid when this is true. And that is, for many applications, it's not true. But it's often a useful approach just to get first results, even though you know at separation, reattachment, this is no good at all. So if you want to be more accurate, then you have to go down to the wall to do the resolution also near the wall. And then you have to use so-called low Reynolds number K epsilon model. So that is the alternative, and that is sometimes necessary. So that has the potential then that you can get more accurate results also when you have separation, reattachment, and more complex flow than just an attached turbulent boundary layer. So instead of wall functions, the near wall region can be resolved and modeled by so-called by a low Reynolds number. Number K epsilon model. So then these equations that I showed you, they get a little bit more complicated, but they keep their structure, say convective flux, diffusive flux, production, dissipation. And you can find more details on that in the book by Wilcox, which is cited in the lecture notes. That is from 93. So that was the first turbulence model devised, two-equation turbulence model, the K epsilon model. But there are also other models, and which have actually some advantages. And another popular model that is an alternative to this one, a two-equation model. Two-equation model is the K omega model. And in here, the omega is essentially, that is defined as the square root of the turbulent kinetic energy divided by L, where L is a turbulent length scale. So, and it is essentially similar to having epsilon divided by K. So, and that is the specific dissipation rate. So the omega is the specific dissipation rate. Why is this, has this a point? Because it's easier to treat near the boundary. So the K omega model has an advantage near the boundary. There, the K epsilon model has a problem with the boundary condition for epsilon. So this is easier with the omega. But the model that is probably used mostly nowadays is a combination of these two models. And this combination is due to Florian Menter, and that is the, so that another model is then the SST, that is the shear stress transport model, sometimes also the SSTK omega model, that is by Menter, 1993-94, and that is a combination of the K epsilon and the K omega model. So the K omega model near wall and the K epsilon model outside. K epsilon model away from the wall. So that is a combination. And that then takes the good property of the K epsilon model away from the wall and the good property of the K omega model near the wall. And you find that essentially in all CFD tools. If you look then next week, we start on Monday on the K, on the star CCM+. You will have it there, you have it in ANSYS Fluent, and I'm sure it is also in OpenFOAM. Okay, so then we have an idea on that. Well, the pros and cons of this type of model, it applies both to the K epsilon, K omega, and the SST model. These are general purpose models. You can use them for different kinds of turbulent flow. And so they have a quite, so I take it for the K epsilon model, but what I'm saying here for that is equally valid also for the K omega and the SST. So that's clearly a plus. It's a general purpose turbulence model. It is not like other models that I will mention later, only limited, say, for aerodynamic problems. So this is a general purpose turbulence model. The wall distance is required when you use wall functions. When you don't use wall functions but low Reynolds K epsilon model, then you are independent of that. That is an advantage when you use unstructured grids. So, and the other thing is it has in general a good performance for many turbulent flows. The disadvantage is, if we compare it now with the simplest turbulence model that we'll discuss in the end, algebraic models, this one is more costly because we have to solve two additional transport equations for k and epsilon or for k and omega. So it's more costly than algebraic turbulence models. And it is known that it gives poor results for curved boundary layers and rotating flows. So they're in general a good performance, but here we have also examples where it is not so suitable. For e.g. curved boundary layers. And rotating flows. Rotating flows. And there are other examples too. And you can find more on that in both the textbook by Fletcher et al. And the textbook that is relevant for this part of the course, Verstegen Haller Sekera. So that is then the two equation models. Now the next point is the one equation models. So that is then C, our numbering, one equation models. So they usually use the transport equation for turbulent kinetic energy. Usually transport equation for turbulent kinetic energy. That is then our equation 14, K, is used, and some algebraic model that we are discussing in the next section. That will be the section D that we are going to look at then, of the mixing length. That is a concept that was introduced by Pranto, mixing length L. That was appearing, I mentioned it before, omega k, square root of k divided by L. This is this mixing length to determine the eddy viscosity. Because if we have the k, then we have the k already for the Boussinesq approximation, which is nice. But what we need also, that is the turbulent viscosity, or the eddy viscosity. And that is then determined by this model as the density, the square root of the turbulent kinetic energy, times this mixing length, L. So that is the usual way. There is an alternative, and the alternative that has gained popularity in aerodynamics, that alternative solves, instead of solving a transport equation for K, turbulent kinetic energy, it solves a transport equation directly for the turbulent kinetic energy. And that model is due to Spallar-Almaraz. Spallar is a researcher at Boeing, and Almaraz, I think he was at Ames. I don't know, he may now also be at Boeing. Yeah. So that is, so alternative one equation models use a transport equation for the turbulent kinetic energy, or for the eddy viscosity. For eddy viscosity, or turbulent viscosity, one uses both names for that, for the ut. And employ the simplification of the Boussinesq approximation. And that is 13, and the simplification is the following. It is used both for compressible and for incompressible flow. So then the Reynolds stress tensor components, which we learned yesterday, are minus density ui prime uj prime average. And the Boussinesq approximation says that we have here the mu t, eddy viscosity, times the j derivative of the ui. So we have the ith component of the mean velocity u bar, and then we take the ith derivative of the jth component. So that is the way that we start, and then we would have here minus 2/3 rho k, and that is simply neglected. And if we have a compressible flow, we would also have a contribution minus 2/3 times the eddy viscosity times the divergence of the mean velocity times the Kronecker delta. And you see what we are discussing is incompressible flow, and we have seen the runs in the continuity equation, Reynolds average Navier-Stokes continuity equation, then this is 0. So then the simplification consists then in neglecting the k in the Boussinesq approximation. So that is an option, and the example for that I mentioned already, that is also available in the CFD tools, is the Spallar-Almaraz model. It is, I think, used quite a lot in aerodynamics. So the advantage of these one equation models are that, especially of this one, for where we have the ut, we don't need a wall distance. That is usually difficult when we have an unstructured grid to find that. With a structured grid it's usually easy to find that, but with an unstructured it is not. So let's see. Just let me finish that. So the one equation models using a transport equation for the eddy viscosity, like the Spallar-Almaraz model. And that is the advantage, as mentioned, no wall distance needed. That was important when people moved to unstructured finite volume method. Then that was, and that is then good for external aerodynamics. And the advantage is it has only one PDE to solve, so that is one PDE less than the K epsilon turbulence model. And however, it is not a general purpose turbulence model. It is more tuned for external aerodynamics. Maybe that they have done now something, but originally it is like that. And it is clearly also, if we compare it with an algebraic model, it is more costly. We still have to solve one PDE. More costly than algebraic models. Okay. So then we have seen now 2 equation turbulence models and 1 equation turbulence model. And then after the break, we'll look at algebraic models.